Welcome to the video for problem 5.3 of Engineering 623. This is a problem with single stub tuning, and it's, I believe, quite straightforward, so let's get right to it. The problem reads as follows. It says, a load impedance Z sub L equals 100 plus J 80 ohms is to be matched to a 75 ohm line using a single shunt stub tuner. Find two designs using open circuited stubs. So here is the Smith chart that we will use, and the steps describing it are below. We begin by finding the normalized load impedance by dividing the load impedance that we're given, Z sub L, by the characteristic impedance of the line, Z naught. So here is our normalized load impedance, 1.33 plus J 1.07. And we plot that as the red point on the Smith chart. You can see that there. The red point here, it just, this location. Now our next step is to draw the SWR circle through that point, which you can see has been done, and then to locate the point diametrically opposite that red point, and we have drawn that as a blue point. And you can see that that has also been done. And this is the normalized load admittance. And now we'll think of this for the rest of this problem as an admittance chart. So we want to move from that blue point along the SWR circle through that blue point. We want to move to the 1 plus JB circle, which is over here to the right. And we see that the SWR circle through the blue point will intersect the 1 plus JB circle at these two green points. So these represent the two possibilities for us in this problem, and the distance that we have to go to get to those green points is we go from the blue point to the green points in the clockwise fashion. The distance that we have to move is the distance from that is related to the distance from the load to the shunt stub. So one distance would be from here to this from the blue point to the upper green point. That's the shorter possibility, and the longer possibility would be given by the distance from the blue point to this lower green point. We find the admittance. In step 5, we find the admittance of each of those points, and then we can, the final step is to determine the susceptance that would be needed from the stub to give us the appropriate final admittance. So to be a little more specific now, if we think of the upper green point as Y1 and the lower green point is Y2, that is admittance 1 and admittance 2, then the distance that we move in the clockwise fashion from the blue point to that first green point, the one that represents Y1, is 0.23 lambda. And on the other hand, the distance we move to get to the second green point is 0.406 lambda. This is read straight off of the Smith chart. Now, as we've identified, the admittance at Y1, the first green point, is 1 plus J 0.99, and at the second green point, the lower one, it's 1 minus j, 0.99. So this means that the stub susceptance that would be needed in the first case is a minus j, 0.99 in order to cancel the plus j, 0.99 at y1. And likewise, at the second point, the susceptance that would be needed would be a positive j, 0.99 to cancel the minus j, 0.99 of this susceptance of the admittance at y2. So let's go ahead and finish these calculations. So again, the stub susceptance needs to be minus j, and this is at the first point, which is up here y1. Since this has a susceptance of plus j, 0.99, the stub would need to contribute minus j, 0.99 to cancel that out. So the stub susceptance needs to be minus j, 0.99 in the first case, and plus j, 0.99 in the second case. And then we can say from equation 2.46c in your book, the input impedance Zn, a distance L from an open circuit, is Zn is minus J0 cotangent of beta L. That's the input impedance. So the input admittance, a distance L from a short circuit, is J divided by Z0 tangent of beta L. It's just the reciprocal of this. And so we want that admittance in the first case to be minus J 0.99 Y naught. And so when we plug that in for Yn, and on the right hand side we write this, and the 1 over Z naught I'm writing as Y naught, so we have this J Y naught tangent beta L. And if we solve for L in this case and take the smallest positive value for L, we get 0.376 lambda. And on the other hand, if we look at the second design, where this is the second green point, where we found out that the susceptance of the susceptance needed from the stub is plus J 0.99. That's the normalized, and then unnormalized would be plus J 0.99 Y naught. And so we set that equal to Yn over here on the left hand side. And again on the right hand side we have J Y naught tangent beta L. And so in this case the smallest positive value of L that will satisfy the equation is 0.124 lambda. So here are our two designs. These would be the lengths of the stubs, and in the first case the stub would need to be a distance 0.23 lambda from the load, and in the second case the stub would need to be a distance 0.406 from the stub. And that is how we do problem 5.3.